The number of data points dictate the grouping in the previous method of curve fitting. Is it the same with the method of moments? Check it out here in numerical solutions to see problems. In the method of moments, the actual moment taken from the dataset must coincide with the theoretical computation of the function, which uses integration. The first moment is then equating the actual h with the summation of y with the theoretical moment of the integral of the function of x. The second moment is also generated with the same concept, equating h with the summation of xy with the integral of x times the function of x. If you analyze these two equations, you would find a pattern that for the first moment is just multiplied by x to have the second moment. Thus, the third moment can be taken just the same, having h times the summation of x squared with y as equal to the integral of the square of x times the function of x. Now, what are these moments? They are actually the equations provided to look for the variables in curve fitting. In case of looking for the best fit line, which follows the format of y is equal to ax plus b, the first two moments will be used to provide for the two equations for the two unknowns a and b. The problem for this last example has 9 data points. But then, since they involve moments only require the summation, there is no impact of having odd-numbered datasets. The initial step is to check the x interval. From the dataset provided, the jump shows 5, so h is 5. Again, we are to look for the best fit line and therefore use the first two moments. The first one needs summation of y, which we can readily compute from the data points provided. The total y in this set is 326.39. From the second moment, we also need to look for the summation of xy, which is determined after multiplying the coordinates. 10 of 5.25 is 52.5. 15 of 9.75 is 146.25. Do the same for the others, coming up with 303, 579.5, 939, 1475.95, 2124.8, 3006.9, and 3982.5, and their total is computed as 12,610.4. Another set of parameters we can take from the dataset are the limits. The lower limit uses the initial x value of 10, then subtract half of the x interval, which is 5, and this gives 7.5. The upper limit considers the highest x value of 50, then add half of the x interval, giving 52.5. After maximizing the details from the dataset, we can then complete the first moment. Plug in values of h and summation of y, which are 5 and 326.39. This is equated with the integral of the function of x. For linear functions, f of x has the format of ax plus b. So the first moment turns to be 1631.95 as the integral of ax plus b. We can integrate these easily after they are simplified per term. So take out the parentheses by distributing the integrand, thereby making a binomial with x dx and solely dx. Having the term simplified, it is easier to integrate them. giving out the first moment as 1631.95, which is equal to the constant a with x squared over 2 plus b times x, the limits of which are 7.5 and 52.5. Next is to take the definite integral and have the coefficients. So plug in the limits, making the moment 1631.95 as equal to a times half of the difference of the squares of 52.5 and 7.5. Add the second term having b times 52.5 minus 7.5. Simplify each term to have the first equation of 1631.95 as equated to 1350a plus 45b. Also process the second moment to have another equation. The left side has 5 times 12,610.4, and this is again equated to the function of x, but this time it is multiplied by another x. F of x is ax plus b, so the moment becomes 63,052 as equal to the integral of x times ax plus b. Multiply terms and distribute integrands to have x squared dx and x dx. After integration, we take a with x cubed over 3 and b with half of x squared. Both terms have limits from 7.5 to 52.5. So if these limits are plugged into x, we have the second moment as 63,052, which is equal to a times a third of 52.3 cubed minus 7.5 cubed. Add the other term with b times half of 52.5 squared less 7.5 squared. Upon further simplification, the second equation is determined as 63,052, which is equal to 48,093.75a plus 1,350b. If one uses a scientific calculator, then it would be easy to look for the variables a and b from the two moments provided. But then, we use method of elimination to show the solution. As we wanted to eliminate b, multiply the first moment by 30 and have 48,958.5 as equal to 40,500a plus 1,350b. Subtract the second moment and have negative 14,093.5 for the constant on the left. The term with a will then have a coefficient of negative 7,593.75. A is then solved as 56,374 upon 30,375, or that is simply 1.8559. Use this value to solve for b from the first moment. This makes the function 1631.95 as equal to 1,350 multiplied by a, which is 56,374 upon 30,375. Then add 45b. By transposing the right term, the function then becomes negative 157,241 upon 180, which is equal to 45b. So b is solved as negative 19.4125. Finally, the best fit line for this problem is y as equal to 1.8559x minus 19.4125.